I'd like to look at a few more examples of coordination compounds, and if there are 4 questions here that we're going to look at. The first one is this one, K2COCl4H2O2. So we're looking at an octahedral complex. I know this because we've got 6 things attached to the cobalt, 4 chlorines and 2 waters. The first thing we have to do is draw the complex and include the charge on the central ion. Right, so what I'll do is I'll show you how to do that. The answers are actually a little bit further on in the PowerPoint slide as well, but I'll draw it out for you. So we need cobalt with 4 chlorines. I'll put all of those in the plane. And then I'll put water here and water here. I want to point out that since the cobalt is positively charged, whatever is attaching to it has to attach through whatever is negative on the compound. And we know through water that O is more electronegative than H, so that's the negative side because it's got the lone pairs on it. So that's what's actually going to be bonding to the cobalt, and that's why I've bonded in that way, with the O's actually bonding to the cobalt. Now we've got 2 potassiums on the outside. That's going to be K plus, K plus. That means that everything in here has to be, has to be 2 negative or negatively 2 charged because that's all positive 2 over here. So now we need to figure out what the charge on the cobalt is. So we know that cobalt plus 4 times -1 plus 2 times 0. Now the 4 times -1 is for the chlorines. They're all negatively 1 charged, and the water is 0 charge. Remember, I get that off that chart that has the ligand field strength on it. There we go, this one here. Cl is negative, water is 0. So you just refer back to that if you need to know the charge on something. Alright, so all of that's got to add up to a -2 charge, and that means cobalt is going to be +2. So that's how we figure out the charge on the cobalt. I'll write that on there, +2. Alright, so we've got that part of it done. Let's look now at how we can get an isomer of that. Now we can't do anion exchange here because I don't have any anions on the outside, so I'm going to have to choose another way to do the isomerism here, and I think I would choose positional isomerism. Here at the moment we've got the waters, they're 180 degrees, but I can rearrange this in such a way so that the waters are not 180 degrees apart, and this actually gives me a different compound, and this is what I mean by positional isomerism. I'll leave that water where it is, this one sticking towards the back, and I'll replace this chlorine with the water, and Cl, I'll be out the front, Cl, Cl, and Cl. The reason these are different is because that's 180 degrees between the waters, and now we've only got 90 degrees between the waters. That's 2 different compounds, 2 different properties. They're isomers. Now we have to use crystal field theory to figure out how many unpaired electrons we're going to have in our complex. And we will look at, first of all, the electron configuration. When we're dealing with cobalt 2+, that's what we're going to be looking for. So we'll do cobalt first, and cobalt, looking at our periodic chart, will be Ar 4s2 1 2 3 4 5 6 7. Ar 4s2 3d7. Now we need cobalt 2+, and as I've explained, The first electrons to go are always the s electrons, and we've got 2 of those, so those are the ones that are going to leave. CO2 plus means it's CO missing 2 electrons, and it's the s electrons that go. So we'll be left with Ar3d7. Now we do our arrangement. And we're going to have dxy, dxz, dyz down the bottom, and we'll have dx squared minus y squared and dz squared up the top. Now we need to figure out what kind of ligands we have attached, and we've got Cls and waters, so we're looking at weak field because we're down pretty much on this end of the continuum. So we're looking at weak field, which means a low energy difference between these two here. If it's a low energy difference, I'm putting 7 electrons in. Then here's how I'll do it. I'll do 1, 2, 3. Then I have to go up here 4 and 5. That's because it's weak field. Had it been strong field, I would have gone down here, but that's not the case. So 5 here, and now we've got 6 and 7. So that would be completed, and this is going to end up having 3 unpaired electrons.